And with that, we can get started. So today we're going to be talking about sort of beam search and a number of variants in the same family. I think so. I think it's recording by default. Yeah. Well, thank you for double checking. So today we'll be talking about beam search and some variants in the same family. We'll talk a little bit about what it means to do a mode-seeking search.
Hey guys, could we quiet down, please?
Thanks, yeah. So we'll talk a little bit about what it means to do a mode-seeking search. We'll talk about beam search in kind of its original form and a number of variants. And then we'll talk about some properties of beam search, including the kind of ominously named curse of beam search. So when we last talked on Tuesday, we were talking about a variety of methods that all look like sampling from some distribution, whether that's the original model distribution or some modification we've made that might change at each step. For instance, if you're doing a top K, the K tokens in your distribution might change over time. So this is a pretty broad class of methods, but today we're going to look at the problem of decoding from a slightly different perspective, which is a little more optimization flavored. So we want not just a good output from our model, but the single most likely output, given the distribution that we've learned over the parameters. So given our evidence and the prior that we have from this model, we want the single most likely sequence. And so this is what we'll call mode-seeking search and what is sometimes also called map decoding, map being for maximum a priori. Now, this is the mode of the distribution over outputs. And if we're sampling just a single token from our language model, this is actually really easy to find, right? If we want to look at this distribution at a single time step, you can take the max by just doing an argmax over your logits, and we're done. This is exactly what we want for a single token output. But if we're interested in decoding more than a single token at a time from our model, if we want a sequence, then this is a little bit more complicated, right? And so this is sort of the baseline that we'll be comparing against today is greedy decoding, where we just take the single most likely token at each individual time step. This is super trivial to compute, but it has a number of sort of problems as we go from sampling or from decoding a single token into decoding multiple tokens. The first of these is that we're not necessarily getting the highest probability output, right? So if we take the sequence that is greater than length 1 and we're trying to find we're trying to use greedy decoding to find the true mode, maybe this works okay for the first couple of tokens, and then we reach a splitting point. And here, this is a little bit of an artificial example, but you could imagine you have two tokens that are relatively similar probabilities at some time step. So here we have eats and Cs. And then the one that has the higher probability at time step t has no particularly high probability completions happening at time step t plus 1. So here, the most probable token at t plus 1 has a probability of 0.1. Whereas the thing that is slightly less probable at time step t could have a really high probability completion at time step t plus 1. And so if you actually multiply this out, you end up with a sequence that you would get from greedy decoding on the top that is substantially lower probability than this sequence on the bottom, which may or may not even be the true mode of our distribution. So this isn't good. If we're trying to optimize, we're not doing a very good job. But greedy decoding can also produce text that looks a little strange. So this is an example from GPT-3. And if you kind of were playing around with models at the time period that GPT-3 was a sort of frontier or frontier adjacent, you're probably familiar with text that looks a little bit like this. This particular example is from a really interesting short story written with some like input or collaboration from GPT-3 called Ghosts, which I've linked here if you're interested in kind of like collaborative writing. But this starts as a sort of reasonable statement or two of turn the space station into a spaceship. And then it starts getting a little bit circular. I'm traveling forward, I'm traveling backward, and I'm traveling sideways. And then if you let it continue, it sort of completely falls off the rails until you're trapped in this loop of just repeating the same 10 or 15 tokens over and over again. Does anyone have a sense of why this might happen with greedy decoding? Or anything about greedy decoding that would make this problem worse? So imagine you start in like a space where you've trained your model over a number of texts, some of which are like good, reasonable looking writing, and some of which are really degenerate things, like just the same character repeated over and over again, or some like really poorly formatted XML scraped from a website or something. When you start getting into a space that is maybe a little bit repetitive, like I'm traveling forward and backward and sideways, you're sort of getting closer and closer to a space of where you've learned the repetitive text you saw in pre-training, right? You've sort of learned that once you see something that starts repeating, generally it starts repeating more. And once you've seen like this, I'm hurtling through the universe and I'm a ghost and I'm in a spaceship once, there's a number of things that are likely completions. But once you've seen it twice in a row, the most likely thing is to see it a third time, and then a fourth time, and then a fifth time. And so maybe if you were sampling stochastically, you could, or if you were doing a stochastic decoding method, you could sample something that's a little bit different from what you had before, and you could break out of this trap. But if you're always taking the argmax, you're kind of reinforcing this repetition, and once you've repeated it twice, you're going to repeat it a third time, and once you repeat it a third time, it becomes more and more likely it'll be repeated a fourth time. And so this is what we call the repetition trap. And particularly for older or smaller models, this is a really common thing to see when you do greedy decoding.
Yeah, and one other comment is this is like particularly frequent in like base models that were trained with maximum likelihood. It's a little bit less frequent in instruction-included models. And it's even less frequent in reinforcement learned models, because if a reinforcement learned model samples these repetitive things, it'll get a low score. And so like you actually have an explicit bias against repeating yourself. So there are ways to fix it through training. But like as I said in the first lecture, you can fix things through training, or you can fix them through inference. So if you have a model that's susceptible to this, you want to use that model, then your only choice is to do it through inference.
I have a question. So what's the snippet of part of the training data? Like the first 3 lines, sentences?
I mean, I don't know the training data of GPT-3, so I can't say for sure, but I don't have any like strong reason to believe.
So my question is that let's say there are like 2 or 3 sentences, which repeat twice.
Mhm.
So we have a total of 6 sentences in the training data. So and now I'm giving the same prompt to GPT-3. So after assuming it repeated twice, is it likely that it will repeat the third time? Because like in the original training data, the next sentence will be something else.
You're saying like if you trained GPT-3 on a whole bunch of versions of the sequence that had like 2 repetitions and then a thing after, would it continue repeating? I think that's a great question. I think it would depend on how, like if you're training it on this exact sequence, I bet you would wind up teaching it that there should be something following after 2 completions, because it would memorize like this 2 completions plus something else structure. I don't know if you could train generally on that kind of data as a way to escape repetition. Yeah, it could work. I don't know.
I'm a little curious about how the probability of the conditional distribution changes after repetition. Like, do the logics where the repetition token is become increasingly trickier as I increase the repetitions? Like,
yeah, this is a great question. So it's as you start repeating, does the conditional distribution change to become like peakier on the logic of the thing that would be the next token in the repetition? I think almost always the answer will be yes, but I didn't actually like visualize it for this.
I wanted to know, as this text is from GPT-3, like for the GPT versions which are like newer, then like if you were to use decoding on those, would like the chance of like probably falling into the repetition trap be lower because of like the RLHF training regimen that I had, or would it just like probably give you a similar outcome?
Yeah, would a better or newer model be as likely to fall into this trap? I think they would be less likely for the reason that you named, because they have been like RLHF and instruction tuned, and also because models that are better trained or trained on more data or larger, I think are less likely to run into this repetition trap to begin with. If you started them on some repetitive text, they would still start repeating, but they're like a very anthropomorphizing way to say this is that the model kind of talked itself into this quarter. of the space. That's not rigorous, and that's not like, but it kind of, you can see it started like doing this like quasi repeating thing before it wound up repeating, because that was sort of like an easy thing to predict as a next token like us. And so a model that is like better trained on a lot of like high quality text, I think, is less likely to start doing that. In addition to like all the benefits of instruction tuning.
Another thing is, like, you might think that there's low quality text that has lots of repetitions, but just think of like all the CSV files in GitHub, or you know, other stuff like this. There's just a lot of legitimate reasons why you would have tons and tons of repetitions. So like, it's not necessarily just the degenerate models that see this all the time. It's like actually good models will also.
Yeah, there's a lot on the internet. There's a great section, I think, of the Dolma paper that has examples of sort of degenerate things they found in reasonable looking places, like Reddit posts with a large number of upvotes that are just the letter M repeated over and over from a subreddit that is about simulating the sound of a microwave going off. So there's a lot on the internet, and we're giving a lot of it to these models. Cool, so these are some issues with greedy decoding. One last one I want to mention is that when you're doing greedy decoding, the model is making a single sort of best effort guess at each step. And so that means if you're trying to decode like sort of some meaning or express some sentiment that requires like a relatively high probability and a relatively low probability word, you can wind up with these kind of like convoluted path of sentences where the dog was seen by Jane is maybe a less fluent or less like naturalistic or smooth way to say this than Jane saw the dog. But because Jane is a relatively low probability token, any entity name is probably a relatively low probability token compared to something like the or dog, it will sort of make the choice that is higher probability until there's no kind of room left in the sentence but to output Jane. And so you can get these sentences that seem like a little bit convoluted or a little bit backwards. So we have the sense that greedy decoding is maybe not the best way to get outputs out of our model, but if we still want to stick with this intuition that we want something that is relatively high probability or close to the mode, maybe as close as we can get, what do we do? And the answer here, at least for today, will be beam search. So the idea of beam search is that we don't want to make a hard top one commitment to the highest probability token. We think there could be something kind of hiding under another high probability, but not the highest probability token. And so we're going to keep a couple of options around so we don't miss something that is relatively high probability that was maybe like the second or the third best path at a previous time step. And the way we do this is a type of breadth first search. So we'll expand at each step into a number of options. We'll prune that back down so that this doesn't become intractable, and then we'll generate a number of candidates for the next step. You can also think of this as a sort of subsetting or like an approximation of Viterbi decoding, which would be a way to exactly explore this probability space if you explored at every step every possible vocabulary token. Of course, this would be pretty intractable if you want to decode more than like one or two steps at a time. So we do this as an approximation. And we're going to step through this in a decent bit of detail, even though I know it's something that a lot of folks have likely seen before, because we're going to talk about a number of variants, and it'll be helpful to kind of keep in mind the details. So we'll start by conditioning on some prefix. Here it is when my cat gets hungry. For reference, this is cat. And we're going to set our beam size to, or our beam width to 3. So we're going to keep 3 completions around at every step. So we take the 3 highest probability things at the first step, which are she, he, and it. And then from there, we expand out to the 3 most probable things following out from each of those lines. So now we have 9 options from our time step 2. And so you read this as just like along these lines, like she meows or it will. These all have a score determined by sort of multiplying the probabilities that we took to get there. And so now we are going to reduce our 9 things back down to 3. So by pruning all but the top 3 most probable things. So here, this happens to be 2 things from sort of our first original beam and 1 thing from our second beam. This could just as equally be 3 things from 3 different beams or all 3 things from the top beam. So now we've got sort of 3 valid paths going again. We're going to expand them back out. There's no particular sort of like mathematical reason. There's no longer probabilities here. It's just getting a little bit hard to see on the graph. And so now we have 9 options once more. We're going to take our top 3, and then we'll expand out again. Notice that now we've got only 6 things going here, and this is because one of the things that we selected at time step, what would this be, 3, is the end of sequence token. So now we have, well, my cat gets hungry, she meows is like a fully decoded potential candidate. And we have, in addition to that, 6 other candidates that are sort of partway through decoding. So now we have 7 options instead of 9. That's okay, because we're still trying to cut back down to 3 options. But now, when we sort of look at scoring these 7 options together, does anyone see a sort of immediate problem with this? Or a reason that this might not be like a fair scoring? I see you nodding.
Probability is less than 1. So you keep multiplying it and the EOS is not getting a fair chance compared to the other field. It has a much smaller sequence which is harder.
Yeah, EOS is not getting a fair chance. Is it getting an unfairly good or an unfairly bad chance? It's getting an unfairly good chance, exactly. So exactly as you said, just repeating for the recording, our probabilities are monotonically non-increasing and generally monotonically decreasing. So anything at time step 4 is going to, on average, have a much lower probability than anything at time step 3. To counter this, we're going to do some kind of normalization of our scores by length. And so here we've been looking at probabilities because they're sort of more intuitive. What we would actually be looking at in a model is log probs, so I'm just going to change those over. And then the sort of simplest way to do this length normalization, and a relatively common way to do it, is to just divide each log prob by the length of the sequence up to that point. So for our 7 candidates here, we divide log probs of EOS by 3, and we divide the log prob of everything else by 4. If you actually look at these, EOS still winds up being kept as one of our potential completions. It's still relatively high scoring here, but as these other things get longer and longer, there's a chance that they'll sort of work out to be higher probability. So we still maintain sort of the possibility of pruning EOS as we go. And we'll continue this until we reach some sort of fixed max decoding length, or until each of our top 3 highest probability beams ends in an EOS token. And then we'll rescore those 3, usually still using this length normalization method, and we'll return the highest scoring of them. Sort of tangentially while we're here, does anyone know why we're usually using log probability instead of probability when we decode? I don't know if we mentioned this yet. Numerical stability, exactly. So our probabilities, especially as we keep going further and further out here, are going to become really, really small numbers close to 0. Our hardware doesn't like really, really small numbers close to 0. And so log probability is a way of preserving the probability and preserving numerical stability. So I said this was a common way of normalizing beam search. It's not sort of the only option. This is, if we view the score of y being just the log probability is the unnormalized score. The version that I just showed you is dividing by the length of y, or the length of the string so far. Another very common variant, and in fact the version that's implemented in Hugging Face, is divided by y raised to some hyperparameter alpha, which I think Hugging Face calls the length penalty. So you can set this to be 0 if you want no normalization at all. You can set this to be 1, or you can set this lower or higher depending on how sort of your prior on what sequence length should be. You can also reframe this as imposing like an additive reward. And then in some, particularly I think in machine translation literature, you can also define some reward that is relative to some length that you expect your output to be. This is not very commonly done anymore, but if you had some strong prior, like you think you happen to know in your tokenizer that most sentences that are 6 tokens in English are usually like 7 or 8 tokens in French, you could impose some kind of restriction so that you wind up with an output that looks close to the length that you think it should be. So this is our beam search algorithm, and to just sort of write out what we just stepped through, we are going to start by making a decision on beam width. And initializing by choosing sort of our top k probability tokens. Then at every step after that, we're going to expand our top k into the k best completions for each of those. So now we have k squared options, or less if one of our beams is an EOS, and we no longer expand from there. Then we're going to prune our potentially up to k-squared options back down to k again, so that this doesn't sort of get out of hand, according to some score function, which is usually the log probabilities plus some length normalization. We all on board so far? Great. Yes?
I was curious if there's any particular way to normalize lengths such that sequences of all possible lengths are put on equal footing. Because it seems to me that no matter the power of alpha, you're like sort of weighting it either one way or the other in terms of sequence length. And is there like some sort of mathematical way to reduce what alpha every possible sequence length is put on equal footing?
Yeah, like is there some way of doing a length penalty alpha or of rewriting this such that every length is put on kind of equal footing? My sense is that this is sort of the price we pay by making our models locally normalized. I can't think of anything that would guarantee. You'd have to know like some notion of true probability that is distinct from your notion of how probability in the model works. I don't think this is possible.
I think it's a good question.
It is a great question, yeah.
Like, how do you mathematically define equal footing is a big question here.
I think the way I put it is that like, suppose I keep a very aggressive penalty, like put alpha to be really, really high, so it's exploding. Then clearly I'll put the shorter sequences on a much better footing than the longer sequences.
Yeah, but in math, what does that mean?
It would be that like, if I can picture every possible sequence length from 1 to infinity should either belong to like the uniform distribution, either there should be like a uniform distribution or perhaps a Gaussian. But like the thing is the Gaussian, I don't know what the mean should be. So just like a uniform distribution.
So this is kind of like what Amanda mentioned with the Amanda mentioned of the like method from machine translation, where basically you say, okay, if I have an English sentence that's of length 30, my French sentence is going to be of length 20 with this probability, 21 of this probability, 22 of this probability. So you can describe a distribution over the lengths that you expect, and then you can multiply that prior into the probability that you get from the language model. And then you can adjust that so that it ends up being the appropriate distribution. So it doesn't necessarily even need to be uniform. It can be any distribution that you define. I can share the paper.
Yeah. But that does require you as the user to kind of define your own prior of what you think like reasonable length is. Okay, so if beam search is great and you wind up with some outputs that look pretty reasonable, but the problem that we'll spend sort of the rest of today thinking about is that you also wind up with some outputs that look really, really close to each other. And the reason for this is that while you're not guaranteed that everything will wind up being from like 1 or 2 beams, on average, you've got sort of some very high probability thing. And if you start with a high probability thing, you're going to wind up with a lot of things along that beam that are also relatively high probability. So this is an example from the first paper that we'll spend some time on today of beam search with beam width 6, doing image captioning for this sort of picture of a train going through the woods. Now, a steam engine train traveling through blank, down, or through is certainly not like the only way to caption this image. And in fact, if you asked 6 people to give a caption, they would probably give you 6 outputs that are all reasonable and look quite different from each other. So we have some notion that like maybe if there's more than one correct answer or more than one reasonable answer, it would be nice to not just look at 6 things that are relatively close to each other, but 6 things that are relatively good that are slightly different. And we're going to look at kind of 2 different ways of achieving this. The first is the paper that this figure is from, and this is called diverse beam search. So if we want to encourage diversity in this procedure somewhere, setting a new beam width is probably not going to help if we think things are going to kind of reduce down to 1 or 2 beams. Choosing the top k highest probability tokens still seems like a reasonable place to start. And so instead, we're going to look at modifying these steps 3 and 4 here. We're going to try to change the notion of what the highest probability continuation is to try to factor in some additional desired criteria, which in this case is diversity or difference from other things. Diversity is kind of a difficult concept to define. And so the intuition and the reason that kind of makes this tractable is that we're not going to define diversity on some sort of absolute level. We're just going to define it relative to what we've done before and then kind of step through this iteratively. So rather than trying to encourage every output to be diverse, we're going to encourage each new output we decode to be different from everything else that we've decoded up to that point. And I'll kind of step through and show what that looks like on a token by token level. So to do this, we're going to define groups of outputs that we're going to decode at the same time. If we set our group size to be 1, we're decoding everything at the same time. This is going to be exactly the same as regular beam search. If we set our group size to be larger than 1, then we're going to decode each of these groups sort of in an iterative fashion. So in our first group, we're going to expand exactly as we did before. So this is the same example, and I've pulled the log probs off because now we're going to be using probabilities that are influenced by or added to like some diversity penalty. So in our first group, we expand exactly as we did before. In our second group, this is the expansion that we would have if we were expanding exactly as we did before, but we're going to modify our log probabilities to penalize things that are too similar to what we just decoded for this time set for the group before. So if you look at this, you see we have she meows and she starts, and we also have he meows and he starts. And so these, we're going to apply a penalty to words that are too similar to what we had before. And so what we'd actually wind up here with is 2 kind of slightly different things, being the top 3 most likely continuations, according to like our modified distribution. So maybe now we get he yells and he is. And then we'll do the same thing with the third group, but now taking into account all 6 things we've decoded before. And here actually these were different enough that we don't need to change anything. So this is sort of the idea, and I've sort of deliberately left what diversity means to be a little bit vague, but we're going to modify our log probabilities such that we wind up with something that is different in each beam group. And then the other key intuition of diverse beam search is that to do this efficiently, we don't actually need to do this like 1, 2, 3, like step through each of these individually at each step. We just need to kind of stagger things through time a little bit. So this is diverse beam search with a beam size of 6 and 3 groups. So in our first group here, we're doing our decoding and we're at time step 6. And then our first group is just regular beam search, so we don't need to condition on anything else. We can just continue stepping through. In our second group, we're doing regular beam search, but we're applying diversity penalties based on whatever we decoded in group 1. So in group 2, we're at time step 5, and we're using whatever we decoded in time step 5 from group 1 to apply the diversity penalty to determine what we'll pull out here. And then in group 3, we're at time step 4, because at time step 4, we've already decided what's in group 1 and 2, and so we can apply the diversity penalty based on what we computed in group 1 and 2. So if normal beam search would have finished in T steps, diverse beam search will finish in T plus G minus 1 steps, because we need to finish each group 2, 3, 4, and so on. This also means that when we prune, we're pruning only with respect to things in the same group. So at time step 6 here, we need to prune group 1 back down to 2 items. And so we'll prune only with respect to things in the rest of that group. Similarly for group 2 when we hit time step 5, and for group 3 when we hit time step 4. So the result of this is that we're doing beam search 3 different times in slightly different settings using these probabilities that we've modified from the groups before. So if we set this group size to 1, this is exactly the same as regular beam search. If we set this group size to be the number of beams, we're functionally doing greedy search in each individual group. We've just modified it by the diversity penalty from the groups before, right? Because we're going to sample the one next thing from each group. And if we set G to be between 1 and the beam width, we're doing beam search within each group, but with these diversity-aware penalties applied. And they find that actually doing this sort of modified greedy search works quite well. So in practice, they set the number of groups to be the same as the number of beams. And then they look at a number of different diversity metrics, which we'll step through in just a sec. But to kind of visualize this out, we've got a number of time steps. We do a single step of normal beam search. which is this line 3 here. And then for every group after that, we augment the log probabilities. So this is our log probabilities, and then we're adding in some diversity penalty from all the groups before. And we perform one step of beam search with our modified probabilities. And then once this completes, once everything has reached the end of sequence token, we return a set of solutions. And you could take if you want a single thing out of this set, you could take the max log prob or the max score. But generally, if you're doing diverse beam search, you're doing it because you want to see all of the outputs of the beams. So how do we actually define this notion of diversity? We have a number of options, and the diverse beam search paper looks at 4 of them. So the first, and the one that they say in practice is actually sufficient, is something called Hamming diversity. And what this does is this penalizes a token proportionally to the number of times it's occurred before in active beams from the groups that we're considering. So if there's 2 beams in group 1, we count up every time the token the appeared across each of those 2 active beams. And we penalize the emission of the token the in group 2 more if it's appeared more times. There's some notion that maybe this is a little bit unfair, that it could be perfectly okay if group 1 is saying the notion at the beginning of the sentence and you want to say the now 20 tokens in. And so they also consider a variant which they call cumulative diversity, which is penalizing only if you're using the same token at the same time step. So if there's in group 1, the tokens the and yell are emitted at this time step, it would reduce the probability of generating the or yell. There's also a variant they consider which penalizes matches of exact n-grams. And the kind of nice thing about this is that this penalizes both individual tokens and also longer sequences. So you can imagine if there's the exact sequence the cat yells has been emitted before, you get some kind of penalty for the cat, some kind of penalty for the, and some kind of penalty for the cat yells. Yes? Yeah. So let's say, I'm just going to say that we have like one thing in group 1, which is maybe the cat. Yeah, actually, let's give it 2. So if these are our 2 things in, can everyone see this if I'm over here? Good, okay. So these are our 2 things in group 1, and now we're trying to decode something in group 2. So group 1 is at time step 4, which means group 2, we're trying to predict something at time step 3. So the cat, let's say 8 is, okay. So if you would see sort of no penalty here for any token that is not in these prefixes here, right? So no penalty if you wanted to generate like meow or something. If you wanted to generate the next token this is like a 2-gram prefix. And so you would get some penalty there for trying to generate something that matches a 2-gram prefix from group 1. If you were trying to generate the cat yells, that's a 3-gram prefix, and so that would be a higher penalty than you would get on this.
Oh, no, I get.
Yeah, sorry, I had to change it halfway through. So cat is matches, but not, and then the cat yells matches 3 things. And so this is the idea that like it's worse to repeat like a full string than a full longer string than to like a single or a double bigram.
So here the prefix across both the groups is same, the cat and the cat.
Mm-hmm.
Could this happen or does this always happen?
Yeah, could it happen that this is the same? This first step actually is impossible. This is a good catch because the first step you're choosing the top k like from a distribution, and so those will all be unique. This second step, like could you decode cat if cat was also decoded above? Depends on the strength of the penalty. So if you set your penalty to be very, very small and there's like a relatively peaky distribution where cat is the most likely token by a fair margin, it could still get decoded.
So my thinking is why not analyze within the group, because from the initial example that you showed, the issue is similarity at the beginning and not what we use towards the end. So if you're not penalizing within the group, then a strong competitor would just carry on.
Why not penalize within the group? Because otherwise, yeah. The reason that they don't penalize within a group is because you want to be able to decode everything in the group at the same time. But I think that this, the question you asked kind of tracks with what they find, which is this intuition that setting the group size as small as possible lets you get more diverse outputs, which is why in practice they set group size to be 1 usually. So this is the notion of diverse beam search, and this is a pretty, yes.
So you said that they said group size is small, right? But if I'm not wrong, you said that when group size is 1, it's basically like vanilla beam search.
When group size, oh, I'm sorry, yeah, they set group size to be as, to be 1, but the number of groups to be large. So when the number of so here, G here is the number of groups, not the group size. So when the number of groups is 1. Cool. So these are 3 of the 4 diversity metrics. The last one they consider is maybe dating this paper a little bit, which is they also look at penalizing things that have overly close word-to-vec embeddings, which is just sort of the 2017 equivalent of penalizing things that are semantically close. And they find in practice that this is not actually worth the extra computational cost. I think this kind of makes intuitive sense if you think about diverse beam searches giving you outputs that are like surface form different, but might still be kind of close to the same semantic mean of the distribution. So that's diverse beam search. And then we're also going to look at another way of kind of getting at the same goal, which is stochastic beam search. And stochastic beam search is based on this kind of nice idea that if you want more diversity, we know how to get more diversity out, which is to sample from the distribution instead of trying to take an argmax. And so we're actually going to do like a very clever trick in order to sample from this distribution in a way that sort of lines up with our other constraints of beam search. So here we've got the beam search algorithm, but instead of expanding the top k, we're going to sample k things instead. The problem is that when we do beam search, we expect that we're going to have k unique things. There's not really a lot of point in carrying across like 5 beams that are all the same token, even if that token happened to be really high probability. So what we really want to do is get k unique samples from our distribution. There's a number of ways we could do this. Maybe the easiest is to just do this iteratively. So if we define like our distribution over v tokens, we sample a single token, we remove it from the distribution and renormalize, and we sample a new token from the distribution of v-1 tokens. We certainly know how to do this, but it's a little bit slow, right? We're going to have to, if we have a beam width of k, we're going to have to do this k times every time we expand out a beam. And so this is, compared to taking an argmax, kind of a time-intensive thing to do. Yes?
How does this differ from just like picking the top k?
How does this differ from picking the top k in one go? So here we're sampling instead of doing an argmax. Yeah, sorry. So this is going to be, we want to sample kind of respecting the probability distribution. Another option, if we want to sample, is we could say, well, we're just gonna sample a whole bunch of things, right? We'll sample a big set, maybe 2 or 3 or 4 times larger than we need, because sampling a whole bunch at once is relatively cheap. And then we're just going to remove everything that's a duplicate, so like some kind of rejection sampling. This is like not a terrible idea, but if our distribution is like relatively uniform, or our tail is relatively fat, maybe we'll wind up with actually a sort of output in a reasonable number of steps here. But if our distribution over next tokens is extremely peaky, we could sample 100 or 200 things and only get 1 or 2 unique outputs. So this is sort of unsatisfying, right? We're not really sure exactly how many steps this would take, and this could be really computationally expensive. There's gotta be a better way. And the better way here is actually gonna take us on a little bit of a detour through what I think is one of the coolest little mathematical tricks that we use today, which is something called the Gumbel-Max trick. Erwin Gumbel was a German mathematician who was particularly interested in the study of extreme value distributions. So the sort of canonical example here is if you're thinking about rain or flood water, like flood water from a river, you can measure the flood line of every rain from the season, but you also care about the max flood line for every year. And so you want sort of the max from this distribution over time. And so Gumbel distributions represent, well, sort of the maximum of some other distribution that you might be sampling from. This is a PDF of the distribution. This is also sometimes called a double exponential distribution because you've got an e to the hanging out in here. And this is what the Gumbel distribution looks like for a couple of different parameters. I don't have the credit on here, but this is straight off of Wikipedia. So here we call mu the location of the distribution and beta the scale. And so you'll notice like a lot of distributions parameterized this way. If you change just mu, just the location, you're going to move along without actually changing the shape of the distribution. You're just going to change its location on the x-axis. So why do we care about this distribution and why have we suddenly taken a little corner, turn into stats land? The Gumbel distribution has this really interesting property, which is that if you take a collection of random variables, xi, and you draw each of them from a Gumbel distribution with location mu I corresponding to that x, you can calculate out the probability, as you would for any group of random variables, that any one of these is the highest valued x in that set. And I'm not going to walk through the derivation here because you're actually going to prove sort of the base case of it in your homework, which will be out later today, I promise. But you can write this out and sort of satisfy yourself that the probability that any individual xi is the max of this group is this e to the mu I over the sum of e to each individual mu I. Does anyone know what this is? This is softmax. And so the collection, so choosing the argmax of this collection is functionally equivalent to taking the softmax over all of these mu I values and sampling one from it. You get something that is sampled from that conditional probability distribution, which means that if you have a bunch of unnormalized logits, you have sort of two ways of trying to sample from them. You could softmax the logits and take a sample in kind of the way we've been talking about for the past couple classes. Or you could add an independently drawn Gumbel noise to each logit and take the argmax of the resulting noised values. And the way this works is your Gumbel noise, if you draw it from the distribution with location 0, scale 1, and then you make your xi's by adding your logits to these Gumbel noises, you wind up, the location is just sort of scaling us along the x-axis, so you wind up with a bunch of random variables that are all Gumbel mu I 1, and then this property from the last slide holds that the max of x is a sample from this softmax distribution. This is, yeah.
The mu is the mean, right?
The mu is actually the mode here. And so it's going to be the top of this peak. It's not exactly the mean of the distribution, though. Beta is like it represents how much this spreads out, how long the right tail here is. So higher beta means a sort of like flatter distribution. But here for the Gumbel-Max trick, we're always going to set it to 1. And this is so that this works out to be exactly softmax.
What are the Zi-Is? How is Zi-Is distributed?
How are these guys? This is just going to be the logits you get out of your language model. So what you would normally do is softmax them so that you get a probability distribution. But we're going to take the unnormalized ones here.
It's kind of magic until you do the math. But it actually works.
I've done the math and I still think it's magic. It doesn't, yeah. So I mean, I don't want to spoil all the excitement from homework one, but what you'll do is you'll take this, you'll calculate like the cumulative density function, and you'll do an integral over it, and a whole bunch of things will cancel such that you wind up with something of this form. It's only possible with this distribution, kind of because you've got this like e to the thing in here.
Okay. No.
Yeah, so on the homework, we're going to have you do this for the situation where you just have two random variables. You can then show it, I think you usually just show it by induction from there. But yeah, I think this is maybe some of the coolest magic that we do. So now armed with a little bit of magic, yeah.
How is mu related to Zi?
Yeah, how is mu related to Zi?
Mu is some function of Z.
Mm-hmm.
How do we know mu I? Like which distribution we are having?
Yeah, how do we know the mu i's? So we framed this in this particular way such that our mu i's were equal to our zi i's, because we wanted to, if we take a bunch of xi's drawn from gumballs of like a group of mu i's, we're going to sample from a categorical distribution. That is what you'd get if you softmax those mu i's. And we want to softmax these zi i's. So we add gumball noise with a location of 0, such that our mu i's will be equal to our zi i's, because it would be functionally zi plus 0. So now, armed with a little bit of magic, we're going to return to our original problem, which was drawing some samples from a distribution without replacement. Why does this help us? Well, we can do this to find the argmax of the distribution. And then if we remove that single thing we just sampled, we say we take the top one away. Now we have z minus 1 things in our distribution. And so we have z minus 1, if we go back, we have z minus 1 random variables here. And so the next highest thing in our set of gumball noise logits is going to be the softmax of this new distribution. And so instead of taking the top one, we can take the top k, and we will get k things drawn from our distribution without replacement, according to that, according to the distribution parameterized by our logits. And that's magic. Are we done? Not quite, unfortunately. So now we've got a good way to sample k things from our distribution. But if we score these k things according to a score function that's just based on log probability, we're going to kind of undo all of our good work here, because then we're just going to choose whichever one of them was the highest probability to begin with, and we might as well just taken the top k log probs. So instead, we're going to try to pass along some notion of like soft committing to a sampled output. We want to carry along the sampling decisions we made to the next step, so that we don't immediately throw out these things that we just worked so hard to sample. But we have to be a little bit careful here, because we want our probabilities to be monotonically non-increasing, and we're now adding noise at every step. So there's some chance we add too much noise and we wind up with something that has a higher probability at time t plus 1 than t, which just is sort of unsatisfying and also does weird things if we're also length normalizing our beams. So we're going to do a little bit of manipulation here. Functionally, we want to carry along the gumball modified log prob. But we want to, so we're going to keep the noise that we added in as part of our final score, but we're going to add a little correction factor such that the modified log probs are never going to be higher than the log probs of the node we sampled from. Functionally, we want to add some noise, but we never want to add enough noise that we go over the probability we started with. And I'm not going to spend time actually going through that, but this is step 14 here. This is calculating, this is the stochastic beam search algorithm, and this is doing the gumball noise, but modifying things such that you're not winding up with anything that's sort of higher than you started with. So if we actually step through the algorithm here, we're starting with these empty beams. We're expanding. Here we initialize the expansions. We pull the log probabilities. So here we take the log probabilities and some Gumbel noise. We keep track of what the highest probability thing so far is by doing this max. And then we go through and we resample sort of for the next step by applying, and we make sure that nothing exceeds the max probability from the step before. In practice, what you wind up with when you do this is a set of outputs that is more diverse, but not necessarily worse than what you started with, which is a really lovely property. So this kind of squiggles on a graph represents at the top the max, in the middle and solid lines the mean, and on the bottom the min blue score, which is just an n-gram quality metric of a group of beam search outputs. Using green is regular beam search, a yellow here, or kind of like dirty yellow, is stochastic beam search, red is sampling, and blue is diverse beam search. How are we winding up sort of so much better in quality than sampled outputs? We're doing a kind of pruning based on this, albeit modified log probability. So we're doing some kind of manipulation to try to make our outputs a little bit better, but because we're also doing the sampling step, we're winding up with outputs that are more diverse than beam search outputs. And this is measured by a diversity metric here that I think is also n-gram based. So we wind up with not just a better top one result here at the very top, but also more diversity and a better average case performance. You notice the top one at this top is not actually very much better than the beam search output. So these kind of like light green up here is actually still sometimes better than the stochastic beam search output. But in both stochastic and diverse beam search, what we care about is less top one performance and more getting a couple of reasonable outputs to look at. So we say maybe we're not gaining on our absolute top one, but we care about this average case or the best n performance. How do you read this graph? Yeah. If you look at the solid lines in the middle, this is the mean of a set of 10 examples. So the mean blue score, average case performance. On top of that, the dotted lines are the max, the best one. The bottom, the lines are the worst one. So this is saying you set beam size to 10 and you looked at your outputs. The average across those outputs will be like kind of okay. The single best one with beam search or stochastic beam search will be quite good, better than the single best one you'd get with sampling or diverse beam search on this problem. And the single worst one for all of them will be kind of similarly bad. Yeah, of course. Yeah.
Also the top peak sampling within each beam in stochastic beam search, because that also kind of improves the stochastic beam.
Yeah, can we also do top P or like some other decoding strategy during stochastic beam search? You could do this. I think what you would need to do is you would need to determine like what you're truncating before you do the Gumbel softmax or the Gumbel top K trick. So you would need to sort of trim your distribution there, and then you'd have a smaller distribution for that. It's a little bit strange. I think you'd have to softmax the distribution to do top P. And then you'd want the unnormalized logits to do the Gumbel trick, so you need to keep them both around. But there's no reason that you couldn't do that. I think like the intuition is good that would reduce the odds of like one of these beams being really bad. Yeah.
What do each of these like points mean? Like, what are they varying along the x-axis?
Yeah, what are we varying along the x-axis here? These are modifying the parameters of the sampling stochastic beam search or diverse beam search to try to achieve this output diversity value of like more or less diverse things measured by n-gram similarity between the beams. So they actually don't specify here what they're doing, but you could imagine this as being like increasing or decreasing temperature for stochastic beam search. Like they might be doing something like top K. For diverse beam search, they're increasing or decreasing the diversity penalty.
Each point corresponds to a particular choice of hyperparameter.
Yeah.
So reading the graph for the same quality of generations, sampling and stochastic beam search shows more diversity. Isn't that what we wanted?
For the same quality of generations, yeah. For the same blue score, you get more diverse generations.
So
Yeah.
we would want to do sampling or stochastic.
So would you want to do sampling over stochastic beam search? I think it depends on what you want. So if you want diversity that's sort of higher than this like 0.22 metric here, you would need to do something like stochastic beam search to get like this increased diversity between nodes. You're paying like a diversity quality trade-off here. But notice that your top one best diversity, or your not diversity, sorry, your top one best blue score is always higher for stochastic beam search than it is for sampling.
Why would I want to use double?
Why would you ever want to use like stochastic beam search here? Oh, the Gumbel trick. The Gumbel trick is what you need to make stochastic beam search work, to make it work efficiently. So you could instead do like sampling iteratively or like rejection sampling. But the Gumbel trick is what we use to make stochastic beam search sort of tractable in the same amount of time it takes to do diverse beam search.
So is there any advantage over just sampling and then introducing randomness and then picking the max like you?
Yeah, like the advantage is that you're doing this within the framework of beam search, so you're also doing this like pruning at each expansion. So you could do the Gumbel trick to just sample from the distribution directly, and that would be the same as these like red sampling lines here. But if you do the Gumbel trick plus this like framework of beam search where you're also like expanding out your set of nodes, pruning down and then expanding out again, you wind up with outputs that are better. You're getting sort of the benefits of doing some type of search. Sorry, I'll come back.
What is DBS?
Diverse beam search is a good question.
Yeah, since you're not using softmax, so how does that impact?
Since you're not using softmax in stochastic beam search, could you still like apply something like temperature?
Yeah, so I mean, I think
Yeah.
you mentioned in one of your answers that like each different point is really at the time. So how does temperature come into picture?
Yeah, I don't actually know. There's probably a way to do temperature with stochastic beam search, but it would be complicated because temperature, you're right, you introduce when you do softmaxing. So to change these like stochastic beam search parameters, they're probably doing some kind of like truncation style modification of the distribution.
Could you just multiply the logic?
Could you? Softmax isn't reversible, is it?
Or maybe I'm missing something, but like, couldn't you?
Oh no, yeah, you could like multiply each logit before you softmax. Yeah, no, Grant's exactly right. So you can think of temperature as like multiplying each logit before you softmax, or applying like a parameter inside the softmax operation. Yeah. Yes.
Isn't temperature implemented as just multiplying the logits before you do softmax?
Yeah.
Yeah, that's one way to do it.
Multiplying before you did the softmax in the normal case, or in stochastic beam search, you multiply before you have the Gumbel ones.
Oh, okay.
Yeah. Cool. So yes. No, you're totally good.
I'm just like a bit curious about that step of yours to limit the amount of noise on each qubit, on each dot probability. Like, how often does it happen? Like, is the Gumbel matrix still valid if you're doing this? Aren't you changing distribution noise every time you apply this value?
Yeah, aren't you changing the distribution of noise when you apply this value?
Yeah.
So the answer is you want to do this only in the pruning, not in the expanding. So you apply the Gumbel noise without any kind of reduction to this max value when you expand. So when you take the top K out of your Gumbel noise logits, you wind up with something that is exactly a sample from the distribution. And then when you're pruning and you're scoring, you need to adjust it back down so that you're not winding up with something that is like a higher scoring continuation at t+1 than it is at t.
I don't like follow that argument because like the whole point of the Gumbel mass distribution is like I can effectively sample from the max every time I make this thing. So the real utility of what we're doing only comes during the pruning stage. So if we're adjusting it before the pruning stage, we like I fail to see how the outputs are still having the same property as the Gumbel max distribution would provide.
Mm-hmm. So how are they still having the same outputs? So you're right that they're no longer a proper like application of the Gumbel max trick at that point. But we need the Gumbel max trick to do the expansion, not to do the pruning. So you could imagine like a variant of this where you sample the top K with the Gumbel trick at step 3, and then you prune at step 4 with the completely normal unnoised log probs. This is like a compromise position. It's saying we don't want to use the Gumbel noise log probs directly because they could have this weird property that they're not on, that they're like potentially increasing over time. Right? If you noise and you wind up with something that's higher than the probability of what you started with. So we don't want to use them directly, but we don't want to completely throw them out because we want to capture some kind of like commitment to the sampling choice we made. And if we just did log probs directly, we would be throwing out all the effort we just did to sample. So by keeping the Gumbel noise, but capping it so that it can't like increase our log probabilities over time, we're kind of like compromising between those two.
So effectively, like, we could get the top K, which is compromised relative ordering between the top K when we apply this threshold.
Yeah, if you had two that were like both above the threshold, yeah. I think that's a good way to think about it. Yeah, for sure. So this is our 2 ways of getting more diverse outputs. We'll talk about just kind of one more set of things, which is a couple of properties of beam search. So kind of one thing that we haven't talked at all about today is how to pick the beam size. And there's like maybe 2 schools of thought here, right? If you have a smaller beam size, you're decoding less things. And you're also, if you were trying to do all of these in parallel, you're sort of keeping less potential paths through your decoding space alive, which means that it's faster. And if you were trying to do all of this in parallel, you're also saving some memory. But this also means you have more search error, right? This is an approximation to exact decoding over the space, which would require setting your beam size to the size of the vocabulary. So the smaller your beam size, the larger chance you don't find the true highest scored output. If your beam size is larger, it's a little slower and maybe more memory intensive, but it's closer to finding the true highest scoring output. It's also worse. And this is like particularly counterintuitive because we should be getting closer to finding the true mode of the distribution. And so this is something called the curse of beam search, which is the idea that on a variety of models, mostly sort of benchmarked around 2018 to 2020 or so, on a variety of tasks that were important at that time, as you increase the beam size or beam width here, the performance downstream actually goes down for sort of the top 1 thing returned from beam search. And there's 2 schools of thought on why this might be happening, and I'll sort of present them both to you. So the first school of thought, and the school of thought espoused by the paper that this particular figure is from, is that this is a problem with our length ratios or our length normalization like not being perfect. Since our probability is monotonically decreasing with length, we're searching more, we're winding up with slightly shorter outputs on average, and for a wide variety of downstream tasks, making our outputs shorter and shorter is actually not very helpful. They show that in some situations, for some tasks, if you can design your length ratio or your length penalty correctly, you can actually get rid of this decreasing with increased beam width. The other argument is that the actual mode of the distribution is somehow degenerate or bad. We don't actually want to find the true mode. And so in some way, these search errors are encoding like a helpful inductive bias that is steering us towards something that isn't the mode, but is kind of helpful to find. And there's some evidence sort of for both of these arguments. So is it clear that the mode is actually what we want out of the distribution? At the bottom of our probability space, it's pretty obvious that we have things that we do not want to find, right? Things that are very low probability, maybe things that are in a different language than whatever language we're currently working in, symbols that are not relevant to us, like random emojis, things that are really unlikely completions. But the things at the top of our probability distribution are relatively close in their quality as well as their probability. And in fact, there's a number of cases in kind of relatively open-ended generation where the probability mass of some sort of like semantically similar thing could be split over multiple completions. So in this case, the cat sat down as our single highest probability completion, but these three things that all mean the cat ran away are all kind of similarly high probability, and between them have way more probability mass. So you could argue that here maybe what you want is actually not the true mode of the distribution. Maybe one of these three would be a better output. We'll come back to sort of this idea of how to find something that is like semantically consistent or consistent in feature space in like a week and a half. But it gets even worse than this. The true mode might be fully degenerate. And in many, especially in older models, if you go through all the effort of exactly searching through the vocabulary space, you get the kind of unsatisfying answer that the true mode is the empty string. And then if we're conditioning on something like repetitive text, the true mode of sort of the distribution past that point might be another repetition, but we might not want another repetition. We might want some other output that is relatively high probability. So we have some notion that maybe the mode is not exactly what we want to find. And in fact, there's this great paper that Daphne wrote when she was a PhD student, which is looking at the log probability of a number of completions for a model relative to some human score of their quality. And they define something they call the likelihood trap, which is that particularly in slightly older models, and particularly in models that were not RLHF or instruction tuned, the top of the distribution, the things that have the absolute highest probability, are less preferred than by humans than things that are still like quite likely. So still we're talking like the top 1/4 of a percentile of probability scores from our model, or of like log probs from our model, but still like not exactly the mode. So the set of things that are sort of most preferred by humans are close to the mode, but are not exactly at the mode. And this is a version of model error. So if our model was a perfect representation of what we actually wanted to decode from it, the things that humans liked the most would be the things that were at the true mode. And so, well, I don't have a version of this figure that's from something like GPT-5. I think there's at least like reason to guess that this might be a little bit less of a problem as our models get better and as we train them with sort of different objectives to get closer to human preference. But nevertheless, this means that beam search, if we get better at finding the mode, we actually might wind up with something that is a little bit less likely, or not less likely, but less likely for humans to like. So if beam search is encoding some kind of helpful inductive bias, or some kind of search error that is useful to us, what might that search error be? There's a really interesting paper that tries to address this argument by functionally designing a exact objective that beam search solves for. They call this the blessing of beam search, and sort of a parallel to the curse of beam search. And if you're interested in this paper is a lovely read. It's called If Beam Search is the Answer, What is the Question? So they argue that beam search with a relatively small size is more likely to enforce a uniform local information density, which they define as the standard deviation of the negative log likelihood of each individual token. This is also sometimes called surprisal in like information theory flavored work. So they show that as you lower beam size up to a certain point, you wind up with a lower standard deviation of negative log likelihood. You wind up with tokens that have sort of more uniform information density. And they argue that this might be sort of a nice property that we're enforcing by accident when we do beam search with a low beam size. I want to take the last couple of minutes here to kind of ask what happened to beam search. So if you've been using a model in maybe the last like 2 years, chances are pretty good that you haven't been using beam search when you're decoding or when you're just sort of hitting an API. People don't really use beam search for sort of frontier models anymore. And while I don't have like an exact answer for you, I have a couple of personal theories for what's going on. As models get better, we're getting better outputs with simpler sampling methods. So this is sort of something we talked about on Tuesday. Maybe we actually, it's less crucial that we very carefully design these sort of token level decoding methods. Maybe we're making less model errors, so this likelihood trap is a little bit of less of an issue. Maintaining multiple beams requires either more VRAM or more time, and this is a little bit cumbersome as models get sort of larger and larger. We also, in the next couple of weeks, will talk about performing search at sort of different scales, over sentences or over paragraphs. And so we're still sort of doing some like notion of optimization over our search space. We're just kind of considering it on a different scale. And then I was thinking about this and I was kind of trying to find examples of this. And if you're interested in software engineer fights, you would love this thread from VLLM, which is the VLLM folks saying exactly what I just said, that we don't use beam search anymore. Is it cool if we just get rid of it? And it's dozens of different people being like, absolutely not. This is crucial for the very specific thing I am doing in industry. If you change this, everything will fall apart and Spotify won't work anymore. Please don't. Spotify is like one of the actual examples in here. And so, well, sort of my instinct was that maybe we don't use beam search anymore. I think this is another sort of academia industry mismatch where in practice for a lot of more specialized use cases, this might be like a perfectly reasonable solution to your problem. So I know we're just at the end of time here, but just as a recap, beam search is a sort of approximate solution to this optimization framing of decoding. We have a sense that maybe getting the exact answer might not be any better than what we're doing. Maybe there's some desirable level of noise or error that we're introducing here. And we can modify beam search in a number of ways if we care more about diversity or about getting kind of a couple of good outputs at once. And homework 1 is going to be out, we think, later today. So keep an eye out for that. We'll post an announcement on Piazza. Cool. Thank you. I can do maybe like questions offline since we're right at the end of time.